I'm Hélène Darnieu, Product Application Engineer working at Teledyne e2v.
And I'm Blake McGill, Field Application Engineer for Teledyne e2v.
Welcome to Teledyne e2v booth. Today we are presenting our ADC and DAC. We have brought on our DD700 board, evaluation board with FMC connectors to allow our customer to evaluate the DD700. So we have a 12 GHz clock differential input, 2 differential outputs, and we also are presenting our latest ADC, the AS940, that is single-ended input and single-ended clock input.
Yep, and so the specific demo we're demonstrating here today is we're doing DVB-S2 demodulation in partnership with Cailabs. So really what we want to showcase here is the capability of our ADC. It has high enough, the sampling architecture is robust enough with high enough dynamic range and linearity to handle a complex demodulation scheme with zero errors, even with what we're specifically demonstrating is non-uniform sampling. So it's taking a subset of the data in a non-uniform way, we're still able to recover the modulation scheme with zero errors. So if you see up here, this is the spectrum. We have 100 megahertz bandwidth at 28.3 gigahertz. We're sampling at 12.8 gigasamples per second. And so you can see up here, this is what the passband in orange looks like after raised root cosine filtering. So very clearly defined passband. And then if we move up here, you'll see the constellation after that, after the raised root cosine filtering, with a EVM frame of under 10%, so well within the range for this mod cod, as well as an ES over N naught of 22 dB. So again, well within the range of the mod cod. And so really quick, I'm going to change this to disable non-uniform sampling so you can see a comparison. This is what it looks like when you have the full raw data being sent from the ADC. So you expect to find clearly defined symbol clusters in the equalized constellation down here. And now what we want to do is we want to reduce that data throughput, the data throughput requirements when communicating to other satellites or to the ground. And so what we're going to do is we're going to enable non-uniform sampling. So we're only taking 25% of the actual data, and we're still able to fully reconstruct the modulation pattern. So I just enabled that, and now you'll see that the clusters have spread a little bit, but you'll see over here, let me move this real quick, we have a zero coded error. What that means is we're able to fully construct the message with zero loss in data and having a clearly synchronized frames here. So what that means is you're able to improve the efficiency of your communication path, reduce power, reduce volume in your systems, thanks to the ADC's linearity and dynamic range. Now that non-uniform sampling is currently in the FPGA, but what we're wanting to do is eventually move that functionality to add that to our already robust embedded function toolkit we have available in the ADC. So that's what we're demonstrating here today, is that our ADC's performance is capable to do that. Thank you very much.